the agreement in the international community, how that might change in 10 years.
Yeah. Economics, I mean, everything I've heard about it over the last few weeks has been economics of oil or economics of Iran now having money to buy things from, well, Italy for one, right? They were meeting in Rome last week, right? So I think economics, again, not my area of expertise, but certainly maybe some of yours, that might be part of it that wasn't in those polls, but that'd be an interesting part of the policy recommendations. Well, good. I'll look forward to seeing how you guys coalesce around some of those key topics.
I just ask a question. Did anybody not get their email? We did? Okay. Oh, you just did it? Okay.
My hope was we could get 10 minutes from one of your classes and actually form those groups with everybody here.
You want to, start waving your hands at 10 up. How's that? We'll just stop at 7:50 today. Would that work?
That would be really helpful.
Okay. Well, then, with the remaining half hour, let's go over some of the technical ideas and concepts that we started last week. Anthony, now could you unlock this thing, or do I need your password? No, there you go. I can do that. So, we left off last week. We talked about things like binding energy, ionizing radiation. We got into forms of decay. I want to go back and make sure I'm covering some of those ideas a little more thoroughly this week, and then see if we can't start to push forward into fission. All right. So let me go over a couple things. So I'm thinking about just discussing the idea of binding energy. I know I started off by discussing that last week, and I just want to make sure that we all have the right scales in our mind, orders of magnitude. And again, we talked about ionizing radiation. I'll talk about real quickly what that means and some examples of it. We'll talk quickly about dose, and then we'll get into fission. So this is a good kind of talking about Einstein, right? The famous equation, E equals mc squared. Until I saw this, as a kid, you know that equation, but it doesn't have a lot of meaning for you until you start doing calculations on binding energy and understanding this idea that mass isn't always converted, that mass is converted, and mass isn't always conserved, it's converted into energy. So when we say binding energy, I know that's a vague term, right? But we're talking about the energy that's put into allowing two particles either to join together and making them more stable, or the energy required to pull them apart. So in this case, this is an example of a helium nucleus. And so the term U is, it's a mass unit. It's an atomic mass unit. And, this is I find it very useful to develop simple physical analogs in my mind to help understand some of these ideas. And I always think of mass as a fundamental particle. It's this idea, to me, it's like a bubble. It's something, the mass has something to do with surface tension. And I'm sharing with you the way I've come to understand this. I'm not saying this is physically correct, but the idea that as you take this space, it's fluid of space, it's empty, there's no mass in it, and you create this bubble, this little thing that's got tension. And it took energy to make that thing, that little bubble of mass, right? It's like a bubble of surface tension. So there's this equivalency between the tension in that bubble and the energy you took to put into it. To me, that's the idea of E equals mc squared. It takes energy to stretch space out enough to give it some mass. Okay, so you got these particles, and they've got some inherent mass now, right? And what's up there? The mass of protons, the mass of neutrons, on the order of one mass unit. And so the idea of binding energy is just like bubbles. You've seen it in raindrops. You've seen anything that has surface tension. You've seen bubbles stick together. You've seen raindrops stick together. Things that have surface tension can, in some cases, want to join up, and they release some of their surface tension by joining together. And some of that surface tension energy is released, and now they have different tension energy. That's the idea of binding energy. You can actually start with 4 separate particles. Here, masses add up to 4.03, blah, 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 U. And when they join together, there's something about the quantum interactions of the fundamental particles that makes these things that before were these tense individual particles relax a little bit. Because now they're stuck together like two raindrops, right? And there's this idea of the the liquid drop model of a nucleus, right? Now these things are stuck together. They're a little bit more, there's a little less surface tension. Instead of having these two things in total surface tension, like two little spheres, it's stuck. And now you relax a little bit. You've relaxed, you have less tension, you've lost mass. And this model that the surface tension is like the mass, you've lost some of that tension. You've actually converted the mass into this idea of binding energy. Right? The combined four nuclei have less mass. And the equivalent energy that's lost, so to speak, is called the binding energy. So that's nuclear binding energy. So really quickly, what's the binding energy of a per nucleon of a helium nucleus? It's right up there. It's roughly right. 4.03 take away 4.00. I mean, I'm going to do this like an engineer, always like an engineer, not like a physicist, which means I'm going to swag it and I'm going to get within an order of magnitude. Factor of 2 if I'm having a good day, right? So we've got 0.03 U, and a U is roughly 1,000 MeV per c squared, right? E over c squared is m, equal density squared, right? So with 0.03 times 931, so that's like 3 times 9, so it's like 28, called 28 MeV, total binding energy, but per nucleon, right? That, you took those four particles, you join them together, you have that much less mass, 0.03 B less mass, that's the equivalent of 28 MeV. Per nucleon, that's 7, right? 7 MeV per nucleon. Now, again, we talked about comparing that to the binding energy of an electron, which some physicist or chemist or engineer or policy major told us was on the order of what? Tens of MeV, right? So that's the idea. The binding, the energy savings you get from binding these nuclei together is so much greater. It's that's your nuclear effect. And that's on the next slide. This is where we started the lecture last week. Comparing chemical energy, the energy that's exchanged between electrons and molecules, which is on the order of EV, to nuclear energy, which is the energy from exchanging nucleons, which is on the order of MeV. 28, just like we said, 28 MeV. M, when I say M, mega, big M, right? I'll mix up a little m and big M. You can call me on it, but in general, you'll know in this case I'm saying big M, mega, 10 to the 6th electron volts. So you can see on the order of 10 to the 6th difference in binding energy. Any questions? Anything I'm getting wrong, skipping over, going too fast about binding energy? It's a pretty key concept. Okay, what's that? So we had this estimate of, so this is the curve of binding energy. Great concept to have in your pocket if you don't already have it. I'm sure a lot of you have seen this before, but this is a measure, this is a plot of a measure of the binding energy per nucleon of the nucleus as a function of the concentrations. And this, in a nutshell, describes why you can get energy from fission and why you can get energy from fusion. We just calculated that, by the way, we were right. If you're somewhere around 4, your binding energy per nucleon is on the order of 7 MeV. What happens when you take two light nuclei and you bring them together, and the resulting nucleus has increased binding energy? You've got the equivalent energy out. What do you call that? Fusion. So that's fusion. We take two light nuclei, have high mass, you bring them together. If you can overcome that Coulombic potential, you bring them together, You get a resulting particle that has lower binding energy, is more stable. As we go up this curve, the nucleon becomes more and more stable, wants to be stuck together, right? So you're getting the equivalent of mass out in terms of energy, right? Everything wants to trend toward iron. At the high end, you see we can get energy out from very heavy nuclei that want to split into various mass fission fragments. The binding energy per nucleon increases, right? We're releasing that surface tension, and so in a very massive nucleus like uranium, plutonium, it's so massive you can think of it almost as just a collection of smaller clumps of little nuclei, and it's this huge thing, and it's like big gum, and it's bouncing around, and at any given moment, nuclei may be forming into little stable clumps, and then unforming and flying around. And, what's the flying around on an incredibly short time scale, right? 10 to the minus 18 seconds or so is a period for a nucleus, right? So these things are moving around, constantly trying to break apart, being stuck together, and once in a while they'll overcome the nuclear force, they'll break apart, and when they do, if one large nucleus breaks into two smaller ones have higher binding energy per nucleon. They'd rather be in that state. You can recover some of the equivalent mass energy. That's the idea. Is that working? So we can fission the high mass nuclei. We can fuse the low energy ones.
That's a really good question.
Sure.
Sorry, just for clarification. So I understand, I see this iron barrier, like this line that everyone uses iron. And it says above iron, heavier than iron, you have fission, and lower than iron, you have fusion. Right, that's like what these are like. So you mentioned, so in this plot it mentioned that the isotopes weren't tightly bound. And I was just wondering if you could give us the intuitive reason why the higher mass numbers would have this fusion and lower mass numbers fission, and why iron would be most tightly bound.
I don't know. I don't know the quantum mechanics of that, but what you said I think was reversed. The heavier ones will fission.
Yeah, that's it.
And so, are you asking why is it convex, not concave, or?
Convex, but I guess how do I interpret this plot and like why? So, like, okay, so the heavier an atom, maybe someone can correct me if I'm really wrong with this, but the heavier the atom, like the more neutrons and subsequently also more electrons. Is that accurate?
Sure.
Okay.
Oh, it's a neutral atom, sure, but
Let's say it's
yeah.
okay. So then the more electrons and also will correspond to more shells of electrons. So the farthest electron will be literally much farther away from the nucleus than the hydrogen atom. So, like, does the actual size of the atom have anything to do with this? Or, I mean, so why does light atom? What's the light atom?
Well, I think first of all, everything that's shown here and everything we're discussing so far is purely nucleon, purely on the nuclear scale, which I think is so many orders of magnitude smaller than the electron orbitals that and so much, 10 to the 6 times more energetic than the electrons. That the electrons and their orbitals and sizes don't matter for this discussion. They do for ionizing radiation and understanding why certain types of radiation are ionizing and others aren't. And as a matter of fact, that's like the next 2 slides I have. But the physics of why it is that as you add nucleons, protons, and neutrons to the nuclear structure, why it is that those combinations start to bind less and less per nucleon as you go past iron, that is nuclear physics. And I'm like, have pity on a poor engineer. I take these results and try to understand them and apply them. That's a great question, and I don't fundamentally know the quantum mechanic answer to that. But I think that's, you get down to how how you describe the nucleons on a quantum basis and how they interact. And yeah, but that's the idea.
So the important parts of this plot are.
The important part of the plot are that very light nuclei, especially hydrogen and helium, can be put into a more stable configuration when they're joined together. If you can find a way to join them together, they would be, they would have, in my little worldview, they would have less surface tension. They'd be two bubbles that were happy to stick together, and what you'd get out would be you'd get some energy back out of it, right? You'd be on your way to making like one big bubble instead of two separate ones, and you make a little wave through your fluid, and that would look like gamma rays or X-rays. It would look like gamma rays, right? But you get a little energy out. They'd say, hey, release tension, gamma rays might fly off, right? And then you can take real small ones and bring them together, you can get some energy out. Or conversely, you can take really big ones that are, bloated. They're full of all these nucleons, too many neutrons, especially, right? And they're just too big. And if they ever can find, just statistically, they're bouncing around so many times per second, right? I don't know, 10 to the 18th, right? That's the time it takes a nucleon to go to ground nucleus. It's like 10 to the minus 18th seconds or so, right? So like insane number of trials that even though the nuclear force generally keeps them together once in a while, spontaneous fission, if the binding energy is low enough, they can pop. And if they do pop, when they pop apart, they're like, what a relief! I have more binding energy. Actually, I'm less tense now. They don't want to join back together, right? If it was the other side of the curve, they'd come apart a little bit, but no, they'd say that's more tense, and they'd want to join back together. If they can ever just pull apart a little bit, they want to stay apart forever, and you get the energy out as ripples of electromagnetic radiation that you can recover. That's the idea.
So we're not going to guess whether it would be fit for nuclei or use it for
That's it. It's new.
But you would be using mass in order to gain that energy. That's the
In both cases, you got to be. You're ending up in a case where you turn mass into energy, I equal density squared. That's the beauty of it. That's what EMC. To me, that's what E equal density squared defines. It describes the binding energy, or conversely, the amount of energy you get out when something goes to a more bound state. Any other questions about that? So of course, we're going to primarily be talking about fissions, somewhat about spontaneous fission, the idea that certain nuclei are just big enough and there are certain quantum combinations that they will, given enough time and trials of bouncing around against themselves in this blob, they'll eventually split apart and give off some energy. Or you can take a nucleus that's close and add in a little extra energy by giving an extra neutron, and it basically creates a excited nucleus that now is very prone to splitting apart and getting energy out. But the idea is you bound it more and you get that energy out in terms of some free energy. By the way, I think about like gamma rays. Any electromagnetic radiation is just some kind of weird vibration of space, right? If mass is a bubble of space where you create this tension, EM is like a vibration, a wave through that space. I don't know what it is, but that's how I think about it. So that's a good segue to this slide. By the way, I stole all this stuff off the internet. I try to be honest about it and tell you where I get it from, no matter how embarrassing the source. But EMX, this is just a good-looking plot, and this isn't that advanced concept. But we did talk about this a little bit last week, and I think it's important, especially if you're interested in the environmental or safety aspects of nuclear issues. You really should understand the difference between ionizing and non-ionizing radiation. So this is where we shift from, very, very quickly, we shift away from nuclear scale to chemical or electron scale, right? So we're ionizing, meaning, in many cases, knocking out an electron from a nucleus. Sometimes it's knocking the nucleus away, but we'll talk about that in a second. So as we discussed last week, as you increase the energy of the radiation, in this case, the electromagnetic radiation, you get to ultraviolet, then X-rays, which are like very similar to gamma rays, except gamma rays are emitted from nuclei, X-rays are emitted from electrons, so clearly gamma rays are going to tend to have significantly higher energy because the energy of the nuclei are much higher. So you can see there's cutoff. There's not exactly cutoff, but it's around ultraviolet, as we discussed last week. I have a sense like you guys, you know that in a way, even if you don't know it, because as a kid, I loved anything that was glow in the dark. All right, and I was wondering how glow in the dark things fluoresce, right? We put them out in the sunlight, and the sun hits it, and it's clear that sunlight radiation, UV radiation, is interacting with electrons in that material. So clearly, the ionizing radiation starts somewhere in the visible or in the ultraviolet. And real quickly, just so you have a scale for that in your mind, there's this idea of the de Broglie wavelength, right? Is that an idea some of you are familiar with? The idea that particles, like waves, can have physical wavelengths. And that's a crazy idea, and I won't go into it, but except to say that you can assign a wavelength to an electron orbital, right? And it can have a wavelength like you can assign to another type of radiation. And the key idea is that energy is going to have a very hard time interacting with other particles that it has a big mismatch on in terms of wavelength. Very low energy electromagnetic radiation with very long wavelength tends to not interact with particles that have very small wavelength. So remember, the cutoff is around UV for ionizing radiation. Ultraviolet, right? UV radiation is at the highest, is on the order of 10 nanometers, right? What's nano? If I say nano is, what's the order of magnitude that you assign for nano anything? Let's see, little n. 10 to the minus 9, right? What's pico? Yeah, so 10 to the minus 9 meters. All right, that's the wavelength of UV radiation. That's pretty straightforward. That's your basic physics class. Now look at this diagram of a simple Bohr atom. I told you there's this idea that you can assign a wavelength to an orbital. So here's an electron wavelength, lambda, and here's the constant of Bohr radius, again in nanometers, 0.05. So let's assume let's assume it's a big, it's a molecule. It's one of the electrons way out on one of the outer orbitals, and let's just say A is 5 or 6 for this case. So say it's 5 times 2, 10, pi is 30 times that number, so it's like 1.15 nanometers, right? So roughly, if I say the wavelength of electrons on the order of a few tenths of a nanometer, maybe as you get on the bigger orbitals, I could farther out orbitals, you can think of a few nanometer wavelengths for your electrons. I say, okay, I can just start to understand that overlap between the electrons on the outside of my atom and UV radiation, right? They're just starting to overlap. The most energetic UV can just start to excite some of those electrons. They can bump them up an orbital, just enough for them to de-excite, and maybe some of them de-excite in the visible light, and now my Dracula teeth glow green for Halloween. That's the basic idea. So that's why we can say there's this idea that below a certain energy, radiation is not going to create ion pairs. It's non-ionizing. I think that's an important point. Now, that's for electromagnetic radiation. X-rays, gamma rays certainly are so energetic that their wavelengths are well below the electron wavelength, and they can easily interact with individual electrons. How would, say, an energetic proton create an ion pair? Any idea? A proton is a it's a nucleon. Basically one atomic mass unit, charged particle. Well, any ideas? Engineering students, and what's the form of interaction for a heavy charged particle through matter?
Scatter off. Atoms in the material passing through, strip electrons off.
Right. It can scatter off of nuclei. So now you can, I mean, it's just if you have a 1 MeV proton come in, it's just dwarfing the energy of the electron binding, right? So it's just coming through and creating massive numbers of electron pairs. So it's a different realm. And alpha particles, of course, are an even more extreme example. That's a hydrogen nucleus, so it's a +2 charged particle, massive force, just plowing through material. What's the range? That's a good experiment. What's the range of an alpha particle? Highly ionizing form of radiation. What's the range of an alpha particle in air, roughly? Anybody? Pardon?
Millimeter? Shorter? I can't remember.
I can't remember. It's pretty short. I know it won't go through a sheet of paper the short way, right? And it doesn't go very far through air. And of course, you do that great experiment where you evacuate the bell jar and you pump it down more and more, and you start to see more of your alpha particles hit your detector. You know, you see it doesn't take a lot of air to stop an alpha particle. That's why they're so damaging. We were discussing last week, and sorry, I don't remember your name, but we're talking about the difference between Rankine and REM, and alpha particles can have a real high quality factor, right? Because they can do a lot of damage, and they can deposit all their energy in a very short amount of space, right? Like in tiny little millimeter track in your alveoli, in your lung, or in your GI tract, they put all that energy in one place, so you have real high energy deposition. They're creating ion pairs like crazy, but that's the idea. That's at one extreme, alpha particles, and heavy charged particles in some cases. And at the other extreme, it would be X-rays, forms of radiation, electromagnetic radiation that are just energetic enough to interact with single electrons. I wanted to clarify anything. We talked about dose last week. This is Nuclear Safety Committee in Canada. I thought it was a helpful chart. What I want to emphasize from this is the numbers we were looking for last week. Annual background dose rate, I think as you said last week, 200 milligrams per year. That's from background. Again, from cosmic radiation, from potassium and radium in the soil. That equates to 0.02 milligram per hour. I tend to think as an engineer who's worked around radioactive materials, handled sources, brought sources out to the field, combined sources in laboratories, and you sit there with dosimeters literally on every finger and you're picking things up. I tend to think about milligram per hour, right? That in my mind, I try to stay away. I'd call one of the technicians over to unload the stuff that was more than about a milligram per hour. I wanted to stay around things that definitely had a decimal in front of them, but because background is 0.02, right, milligram per hour. If you look at this chart, you can see 10 cross-country flights will give you, let's see, give you 2 milligram, and that is a percent of your annual dose. Maybe we can find a way to pass this out later, but
you upload these slides, yeah,
pardon?
yeah, the people put them.
Yes, yeah. Oh, yeah. Oh, okay. Yeah. Of course, there's differences between occupational limits and public limits. So I just want to provide that to you guys. Let's see. So that's it for the slides.
Just a policy-related comparison. There's more radiation dose, or you receive more radiation dose in capital buildings.
I've heard that kind of stuff. I know I have to stop in 3 minutes, but I have a hard time believing that. I mean, there's norm, that's granite, different types of granite. I've driven around the national capital region in the vans measuring stuff. It depends on where you work in the nuclear plant, I'm sure.
Yeah.
I'm sure I've gotten a lot more radiation working on some of the things I've worked on than I would standing around a building. The pink granite seems to be the most radioactive in my memory. Interesting point. Honestly, here's why background radiation doesn't bother me, even if it's slightly elevated, because in my mind, somebody should do the calculation for extra credit or something. When life evolved, hundreds of millions of years ago, the potassium and uranium and radium was much hotter. Like we're on a much, I don't know how old you're, for a billion years or something. But here when life started, roughly, like we're many half-lives down in radioactivity since things got going here. So you got to figure we evolved in a more radioactive environment than we're living in now. So that's what I tell myself when I go to work. All right, one last thing. I'm going to use maybe a couple of your minutes. I know you're going to break into groups here. Half-life. I want to hit on some of the key concepts that constantly come up, whether you're a policy person or a technical person. And I want everybody to understand, I want everybody to see the derivation of the concept of half-life and understand it completely so that, like, again, whatever meeting you're in and someone discusses radioisotopes and radioactive half-life, you feel totally comfortable with it. And what is the idea, can anybody tell me, what's the idea of a half-life?
How it takes for material or half that material to decay away.
Right, through natural decay. All right, so when we talk about radioactive decay, we talk about the number of nuclei in a sample. So if I take a sample and it's got N nuclei, atoms in it, it's got a billion atoms, whatever the number is. You'd say, what's the rate that number of atoms will decay at? What's so special about radioactive decay that lets us calculate half-life? The rate of decay is proportional to the number of nuclei itself, right? Right. So the number at any given time is equal to I'll do it this way. The change at any given time, right? The rate of change in the number of nuclei is equal to a constant times number of nuclei. Is that right? And this, of course, is a minus sign here because it's going down. The rate of change, right? The more you have, again, you got a room with 100 unstable balloons in it. That's not very many. You're going to wait a day, one's going to pop. You're going to wait a day, one's going to pop. That's fine. The rate is proportional to that 100. If I put a billion balloons in a room, and listen, it's going to be going pop, 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 pop nonstop. I just have a lot of balloons, right? So the rate of change is proportional to the number you have at any given time. So I won't even up any more of your time, but someone be ready to come next week and derive for me half-life from this and show me how we create a really simple expression for calculating half-life, because it's very helpful. You don't have to go through this every time. You get a shortcut. Nature gives you an easy shortcut. It's one number you have to remember, and you're done, and you can always calculate the half-life. Or you can calculate the rate constant. So, take that as a homework assignment. Some of you guys will do it before you leave, and obviously the task is to find the functional form for NFT. But I have used up more of my time. So that, I guess, I'd ask you to keep reading. We didn't get to fission today. I wanted to be able to start getting into the concepts of fission reactors, because for the semester project, you've got to understand how reactors work and what's going on with fuel irradiation. You've got to understand fuel processing. You've got to understand enrichment. we've got to get into the engineering parts of reactors and eventually nuclear weapons. So please read in the assigned chapters in Lamarche, chapter 3, most chapter 3. If you're not an engineer person, feel free to ask questions. You can send emails, and my office hours are 3 to 5. But I'd really like to take a big step forward next week and start talking about reactor engineering. Thanks a lot. So you have 7 minutes for your group discussions.
So anybody who wasn't here, you guys have the document.
Okay.
Yeah, we're really small,